Hello, everyone. Welcome to the 12th and final live session for the course Foundations of Our Software. So far we have had these 11 sessions. This is the 12th one. And before the exam, we will have another revision session that's going to be on the 21st of October, Monday, same time. And do any of you have any questions before we start today's session? All right. So if there are no questions, then let me start with a revision of what was covered this week. So, before we head into this, yeah. So I hope you can see the screen all right. All right. So for today's class, we will be taking. So there'll be two data sets that we'll be generating, and we'll use that throughout this session for today. So as you can see here in these line number 5 to 8, we are defining 4 vectors. And this is the demographic of a place and demographics of the 50-year plus population. So it's just a made up data set with these are the ages arranged in alphabetical order of the rural male population, the rural female population, urban male, and the urban female population. So I'm just going to run these 4 lines. And you can see here that depending on what the distribution, what the number of people are, the number of elements in each of these vectors is different. For convenience, I've arranged this in ascending order, but it need not be arranged, right? When suppose a survey is taken and when ages are recorded, they need not be arranged in ascending order for this work to be done. But just for simplicity's sake, I've arranged them like that. Okay. Now, these 4 vectors, what we can do is we can make a data frame out of them, but this data frame is not directly going to be this itself. But what we'll do is that there are going to be 2 columns in it. The first column is what each of the group represents. So what we are saying, we are calling it the column as group, and we'll say you repeat these 4 values, the four categories, as many times as is the number of each of these vectors, as is the length of each of these vectors. And then in the ages column, we write the actual ages. So to show what I mean, I'm just going to run this line and we'll see what this data frame looks like. So you can see here we have 2 columns, group and ages, and group is whatever the one of the 4 groups it is, and ages is the corresponding age. Okay. So we have, if you sum up these 4 vectors, the length is going to be 76, and that's what the dimension of this data frame is. And also, since the first column here is a categorical variable, so we can define it as a factor. And if you remember from our previous discussion, this is how you'll define a factor. You give the vector or give the column which needs to be converted to a factor. And if you have a particular preference in which you want the factors to appear, you give that as the levels argument. So I'm just going to run this. It's not going to make any changes to our data frame, not visually, but internally, if you look at the structure, this column is a factor. Okay. Now, I'll take a slight detour and I want to demonstrate one thing here. Okay. So through towards the end of this week's this session, we will use something. So you're familiar with what a histogram is. So we'll just see how we can make that from this data set. So let's say we want to, 1 second. Okay. So let's say I want to convert, okay. Yes, now it's fine. Okay, so let's say I want to define these groups. So between ages 50 and 55, then like greater than 50 up to 55, then greater than 55 up to 60, greater than 60 to 65, greater than 65 to 70, and greater than 70 to 75. So, right. So what we do for a histogram is we divide the range into adjacent or joined categories, ranges, and then what we can do is we can count how many values are there in each of this. So between 50 and 55 you have these two values, then between 55 and 60 there are these four values, then there are these next four values in the category 60 to 65, then four more four more here, and then the last five are here. Okay, so 2, 4, 4, 4, and 5. This is how many values, or in this case, how many people there are in each of these age ranges when you're talking about the rural male population. Okay, now what we can do with this information is we can define these categories. So category of ages, these 5 ages that we talked about. And for each of them, we can have a set of 4 values, where the first value indicates how many people are there in the rural male population, then how many people are there in the rural female population. Next one, how many are there in the urban male population? So that's going to be these here. And then finally, how many in the urban female population, so which is like this. Okay, so this activity, if you do it for all the 4 groups, then you can define something like that. So I'm going to define these 5 new vectors again. And with these vectors, what we can do is we can make a matrix out of it. We can also make a data frame, but the main advantage of a data frame over a matrix is that you can store multiple types of values. But here we just have numeric values, so a matrix should also be enough. So again, nothing fancy. We'll just make a matrix with this vector, right? So the first value that you give for a matrix is the data. So you're giving like a matrix, this vector of vectors here. So it's just going to make a longer 40 element vector. Sorry, yeah, 4 into 5, 20 element vector. And then you can fill it by row. The arrangement is yours. So in this case, what I've done is that you fill it by row, and number of columns is 4, number of rows is 5, just the way it's looking. And what I can do later is I can define column names and row names for this. So the column names here are going to be the 4 categories, and the row names are going to be the ranges that we're looking at, right? So if I run these 3 lines and if I see what the demographics to matrix looks like, this is what it is. All right. Any questions up till this point? So here we have defined these 2 data sets, or these 2 data frame and matrix, and we'll use this throughout the examples to sort of revise this week's topics. So any questions, any confusion? I can't hear you. Maybe if you can type it in the chat box. Okay, all right, great. Yes, so in case you have some question, I'm not sure if there's some connection issue from your end or my end, but I'm not able to hear you. So you can still just type it in the chat, and if it's a longer question, we'll get to it. Okay. All right. So now a large part of what was covered in this week was plotting the data. So we'll start with a simple bar plot. This is also something we saw in the last week. So mainly to make the main type of bar plot that we'll be looking at here is in the x-axis, you have some categories, and in the y-axis, you have the corresponding frequencies. Okay. So the main difference between a histogram and a bar plot is histogram on the x-axis, you have a continuous range. Okay, these are generally numbers themselves. These are not categories. But for a bar plot on the x-axis, you have categories. Okay. So in this case, what we can, out of these 2 data sets, the first column in demographics 1 is what we can call as a data set which is suitable to make a bar plot from. So we'll use that column, the groups column here. And then we want to find out how many occurrences are there of each of the categories. So to do that, we use the table function. So if I just run this bit, just the table function. So we had seen this in one of the earlier classes, that this is what it does. It takes each of those variables and it just counts how many occurrences are there of each of them. So you've got a frequency distribution, or like just the frequency of each of these. Now we use this as the input to make a bar plot. So mainly to make a bar plot, the input has to be of this format. And this is nothing but a named vector. So if I take the structure of this thing, yeah, no, it's a table. Okay. But mainly what we need is that there has to be a name and then there has to be values. So we will see what else can fit into this description. But okay, so we've got this table and we'll make a bar plot and just, so this is also something we'd seen in the last class. The main aspects, the main other arguments that you can fit in for plots, mainly there's going to be a title. There could be x-axis labels, y-axis labels, something to do with the legends, fonts, font size. So, but still one of the main thing that each plot should have is a title. So for most of them, it is given by the argument main. All right, so main is equal to, and then in double quotes you write. So just for simplicity, we are writing plot 1 here. So if I enter this, now the plot is by default, it's going to come up here in the plots pane. For our studio, it's both good and bad that this is quite modular. So we'll see what it means, but you have to ensure that the space here is big enough. Since I have increased the font size a bit, so the font here is going to be a little big as well. So you need to ensure that this has enough space, otherwise it can throw an error. Okay, so let me run this. So now you can see here it looks okay, but some things are missing here. So if I just expand this, you can see that R is now able to fit in all the things it wanted to, so it's looking okay. So, but you can also zoom from here and it opens up in a new window, and then this looks a lot more legible. All right, so what it's doing again, so this was the data that we were looking at, right? So rural male, whatever number, so that was 19, 14, 24, and I think 19 again, something like that. So that's good. Another data that we can make a plot, a bar plot from is the demographics 2 data. Now, if you think about it, if I take the sum of each of the columns, so I take column sums or col sums, then it should give me these 4 values again, right? So this, if you add this up, so it's giving you 19, 14, 24, and I think 19 again, right? So I can do a call sums. Now this, I'm not doing tables, so I'm not getting a table as the output. But again, what you see here, it's again a named vector. So the names were coming from the columns and the value is that column sum. So if I give this as the input to the bar plot, now you see the title is what is indicating that the plot has changed. So it's now plot 2. It looks identical, but these are different plots. Likewise, from this one, we can also take sums of the rows. So what is that? So that's going to give us that throughout the population, how many people are there in each of the age ranges. If I run this one here, so you can see here I get a new plot where now my categories are these age ranges, and the columns are indicating how many people there are. Now, again, a very minor difference, but for a matrix, you can always transpose it. You can take the transpose of the matrix, which is basically you're switching the rows and columns, right? So what I've done here, I've transposed the matrix and then I've taken col sums, which means effectively I'm taking the row sums of this matrix, right? You transpose and you take a col sum versus for the actual matrix, you take the row sums. It's the same thing. So if I run this, I again get the same plot, but you can see here it's now plot 4. again, this is not very important, but it's just to indicate that the different ways in which you can, which different inputs, different forms of inputs can be given to the bar plot function. All you need is to ensure that there is a name and a value in that variable. Okay. Now we can make something known as a stacked bar plot, or it's called as a subdivided bar plot or a component bar plot. So what I can do is this demographics to data, if I directly give it to the bar plot function, I don't take row sums or col sums, or I just don't take one particular row. If I'm giving the entire matrix itself, so we see what it does. It's sort of plotting the matrix itself. So you can see here. Okay. So for the sort of rural male population, this value 2 here, that's indicated by the darkest color, which is at the bottom. Then these 4s, which are in the decreasing gray colors. And then the last value here appears at the top with the lightest shade. But anyway, the coloring is a default scheme. But the important bit is the rows. So 1, 2, 3, 4, 5 rows appear here from bottom to top. Right? So this is there. And of course, oh, sorry. So again, for this one, we could have also taken the transpose of that matrix. So can you think what would be the categories if I take the transpose of the matrix here? Right now, the categories are the columns that the columns are, right? Rural male, female, urban female. If I take a transpose and then make a bar plot out of it, what is that going to be? So by default, the columns are taken as the category. So once I transpose the matrix, these rows are going to become the columns, and hence they are going to become the categories. Right? So this is what it looks like. Now again, so you can see here that, for example, in this group, the 55 to 60 group, there's 4, 1, 5, 1. So there's this 4, then 1, then 5, then 1. Okay. So now, of course, we may want to we may want to provide a legend. So what we can do is we can say legend.text, and that is equal to, so again, back to this example. So here, each of our colors are indicated by the rows, or each color is indicating a row, right? So the legend is going to tell us that the row names from this matrix have to be provided. So if I run this one here, so you can see here it shows up a legend. It's overlapping with the plot, but that's okay for now. So you can see here that what color is indicating what ages, that's provided here. So the first row, which is 50 to 55, that's appearing at the lowermost, and it shows the right color. So that's important. Then of course we may want to provide some different colors. So again, whatever number of categories there are, or I should say whatever number of subcategories there are, so there are these 5 subcategories which have to be assigned colors. So we can provide 5 colors. So with the call argument, you say call is equal to, and then within a vector, you give names of any 5 colors that R is able to recognize. So mostly any color that you can think it would be there. But I've just taken 5 basic colors. All right. And then if you want to change the position of the legend, this is what the color thing is going to look like. If you want to change the position of the legend, the argument here is args.legend is equal to list x is equal to and wherever you want it. So again, this is a little bit complicated, but this is what the syntax is. But again, don't get too bothered about this for now. So if I use this, if I put it as left, then this is where it's going to come. Okay. And then also you can make a you can make a pie chart out of categorical data. If you don't want to make individual bar plots, you can make one pie chart for the whole thing. So again, just like we did initially here, so you made a table and then fed that into the bar plot function. Now you can feed that table into the pie chart function, which is pie. So if I just run this one and this one, these are comparable, right? So here it's the relative. So here the bars are both indicating the relative differences across these four categories as well as the absolute frequencies. And for a pie chart, you only get the relative abundances, not the absolute abundances. So again, it depends which plot serves your purpose, but they're both using very similar syntax. Okay. Any questions so far? Okay. All right. All right. Great. Perfect. So both the bar plot and the pie chart here, we were more focusing on the categories and not the actual values of those ages, right? So now we can shift our attention to those continuous variables or the quantitative data. And we'll start with, or we'll mostly be focusing on making a histogram. So simplest, if I take the demographics one ages column, and I simply feed that into the histogram function, which is hist. So this is what it's going to look like, right? So it's automatically divided it into these groups. Now, I did not feed it that it needs to make groups of like ranges of 5 years apart, but it's made it that way. So there is, I'm forgetting the name of the algorithm that is there in R, which determines how many breaks there are going to be. If I remember, I'll let you know. But again, so there is a default inherent value that it takes. So in this case, it's divided them into 5 ranges. And by default, what it plots on the y-axis is the absolute frequencies. So between ages 5 and 55, there were maybe whatever 7 or 8 individuals, and then there were about 11 individuals in this, and so on. If you give it this argument, frequency is false, then this histogram, the nature of the histogram remains the same, but instead of plotting the frequency, plots the density. And what I mean by plotting the density is that the area of these of these 5 bars, if you say, so area is length into breadth, if you take the area of each of these 5 rectangles and you add them up, that's going to give you 1. Okay, so that's a density or a relative frequency distribution. And by default, or if you had frequency is true, then you're getting the absolute frequency. Okay, so they're both the main ways in which you can use the histogram command. And so typically it's not very commonly used for the basic plots, but this is a useful application. So if I just simply type the command here, it's going to plot the command, right? But what I can do is I can assign the plot to a variable. So if I run line number 49 here, so you see it did plot, but also it got saved here. Yeah, so since I decreased the margins, it says the figure margins are too large, so it's not able to plot it. Now it's back. Okay, so I got this variable h. And now what you can see, it's just to give you an idea. So what is actually being done internally when R is making a plot is that given the data, given the ages data, it's able to make these new variables. It's able to do some calculations. So it's able to make these breaks. So whatever the internal algorithm was, it made these breaks. It made counts for between each of these breaks. So between 5 and 55, there were 7 individuals. Between 55 and 60, there were 11 individuals, and so on. And corresponding density was this, right? So if you add them up, and so 7 divided by the total, that's going to give you this. And then what is the middle of each of these ranges? So that's just to sort of give you areas and stuff. So that's there. X name here is the x-axis label. And equidistant, I think this is that each of your breaks, they're equidistant. They are not in different ranges. So internally, these are the values you need to make a histogram. Okay, anyway. Now, some of the other arguments that you can use for a histogram function is increasing or decreasing the number of breaks. So here by default, there are these 5 breaks. Now, if I say breaks is 10, it's going to give you this. So sometimes, so when I've given 10 here, it's giving us more than 10 because that would mean it can't divide them into exact groups. So it would estimate it to be something around 10. But basically, we've increased the number of breaks here. Sometimes you may not want to plot the entire thing. So even though your data was between 50 and 75, what you might be interested in is just looking at how things are between 50 and 60. So if I can specify that. So it's basically just plotting between 50 and 60. Everything else stays the same. The internal calculations would still be as they're done for the total data, but you're just plotting the data between 50 and 60. So you see here between 50 and 55, there was the original, again, it's the original breaks here. So that's every 5 years. So 50 to 55, 55 to 60, and then you've not plotted the remaining bit, but the number still stays the same. And if you increase the breaks, then of course, there are going to be more breaks here. So that's there too. Now, what is happening at the moment is we're making one plot for the whole area, right? Now, this is good because it's giving you a larger area to make the entire plot. But then if I have to compare one plot with the other, I'll have to keep switching left and right. So what I can do is I can also make multiple plots in the same area. And for that, you just need to specify how many plots you want and in what arrangement. So remember when we have been talking about 2-dimensional variables, whether it's matrix or data frames, you can specify rows and columns, number of rows followed by number of columns. The same thing happens here. So there is a par function when you want to organize more than one plot in the same area. So within the par function, you give it the mf row argument, and you say mf row is equal to, and then as a vector, you give it the dimension. So here, what I've written would mean that I need 1 row and 2 columns. So once I run this, you don't see a difference. Nothing's happened right now. But then let me plot this one. So this one we had seen earlier, right? The ages column, and I want to make a histogram. So now if I plot this, you see it's just plotted in the left half. It remained, the right half is still empty. And then when I make a bar plot, I make just another plot. It's one of the same bar plots that we had seen earlier. So if I run this, now that's plotted on the right side. And you can zoom it, it still retains that organization. And so another reason why we've plotted these two together is you can see that they're both conveying the same information. Okay. So for a continuous data, definitely a histogram is a more accurate descriptive plot. But because here we did not have to do any calculations, right? We just fed it the ages column and that's it. This bar plot was made from demographics 2 matrix, for which we had to actually calculate values from within each of these ranges. So here there had to be a manual job done. But for the histogram, R did that internally. So a histogram is a better description, but both of them are equally correct. All right. It's just another example. So if I run this command, how many rows and how many columns are going to be there? How many plots are going to be there in all? Okay. Yes. So this one says that 4, 3. So it means there are 4 rows and 3 columns. Right? So a total of 12 plots can be fitted. You don't need to fit all 12 of them. So again, let's say I just make, I have 10 plots with me. So I run these 10. Oh, sorry. This one. Let's see, it's too large. Okay. So still large. Does it work now? Nah. Okay. So this is sort of working. So you can see here it's making 3 plots in one row because I said there have to be 3 columns. So 3 columns indicate, like, in each row there are going to be 3 plots. And then the 4th plot goes into the next row. And then the 5th one, 6th, 7th, 8th. Now that's it. Let's say I just want, or maybe I just want this much. I can save this. I can export it. I can save it as an image. I just say trial. And then here it should open up. Figure margins too large. Okay. You can save this. Let's just plot something. Okay, never mind. So we'll discuss in a bit how to save these plots. But yeah, so the main thing here is if you can specify how many rows and columns or what sort of an arrangement you want, and then you can plot. And just another comment here. So here, if you want to make the same plot, but just the names are different. Yeah, this was the size issue. So I'll let you know in a minute how to save the plot. Had this been like fewer plots, maybe just 2 or 3 or 4, then it should be okay. So there's a better way. And anyway, okay, let's see what that is. So there are different file, like, image types that you can save. So if I want to save, let's say, a JPG file, the function is going to be JPG. And within double quotes, I can specify. So in my working directory here, I can just give it a name. So I'll just say image save dot JPG. And then I can give it the width. So I think the default width is in pixels. So maybe I'm just giving it a random value. Width and height, let's say 3000 by 3000. And you can also give it the resolution. So 300. So once you start this function, okay, you're giving the name of the file, the dimensions, the resolution, and then you give it the actual printing command. So what I've done is you specify what arrangement of plots has to be there. And then here, just to simplify, instead of saying that, plot histogram 1, plot histogram 2, up to 12, what we can do is use a for loop that we have seen in the past. For I in 1 to 12, you're making this histogram. And what I'm doing is, as the title of each of the histograms, we can use the paste zero function. Remember, the paste zero function pastes, like, let's say 2 values, and they're not separated by any spaces or any character. So it's just going to become histogram and I. So histogram 1, histogram 2. So you see, this saves up a lot of space. And once you have done the actual plotting, this is important. You have to switch off that device. So here the device is, the way this works is you are opening this image, you're printing something in the image, and then you want to close. All right. So I run these commands all together. I think the function is JPEG then. Okay. So if I run these things, all right, sorry, yes. Okay, so this looks fine, right? So you can see here that you have histogram 1, 2, 3, 4. These are identical histograms, just the title has been changed to indicate that these are indeed different plots. And this looks fine. Now, if you want it to be in a slightly different shape, if you want it to be a little more landscape, you can increase the width to maybe 4,000. And then, so you can save the image like that. A simple way definitely is through the export function, but for a little complicated ones, it may not work fine. So this is definitely a go-to method. Now, instead of the JPG function, you can save it as a PNG, as a TIFF, as a SVG, which is scalable vector graphics, depending on whatever the use is. And by default, since you opened, so not in this case, not in when you're using a JPG file or any other file, but when you have opened this in R, in the plots pane, you would like to sort of switch it back to a 1:1 arrangement, right? So you can just use the par mfroc11 command. And yeah, so once you've run this, it should, now whenever you make a new plot, it's not going to plot here, but it's going to make a simple one plot in that area. All right, so let's take a look at another type of data. This again, we saw a little bit in the last class. So there's an inbuilt data set in R, it's called the trees data. And it's giving you, I think it's for 31 observations, the girth, height, and volume of the trunk of the trees. So now if I just, so the plot function is the function we'll be using. If I just plot one of the columns, okay, whether that's girth, height, or volume, whatever that is. So you can see here that by default, the x-axis is your index. So index is nothing but the order in which that data was coming. And the actual data is being plotted as the y-axis. So you can see here that the first index here, the height was 70. For the second index, the height was 65. For the third index, it's 63. Yes, the digital calculator is going to be available. So you would have received an email, and it's there on the announcements page of the NPTEL course. There is a sample calculator link given. Yeah, okay. Okay, so this is what, for this scatter plot, if you're just plotting one variable, by default, R is going to plot it index versus the value. And you can see here, we did not specify what the minimum and the maximum for X value or X or Y values are, right? But this is sort of internal, that it's going to take some values a little less than the minimum, and it's going to have a range like 1 or 2 values more than whatever the maximum is, so that the plot looks good. But of course, you can specify the X limits and the Y limits, and we'll just see how you can do that. Typically, for a scatter plot, you would have paired data. So let's say if you want to plot the girth versus the height, right? So, or any two variables for that matter. The important bit here is the first value that you give, that becomes the x-axis, and the second value becomes your y-axis. Okay. So now you can see here, if I'm plotting the girth and volume, so the first one becomes the x-axis and second one, the y-axis here. And you can see there is an increasing sort of 1:1 trend here, which is expected. Okay. Now, there's one more thing here. Now, instead of using so x comma y, instead of specifying x comma y, if I say one value and the symbol tilde, which is left on the left, towards the left of one on your keyboard, on the top left of the keyboard, if I plot this, so value 1 tilde value 2, then it's not x versus y, but then it becomes y versus x. So this is your xy plot, and this becomes your yx plot. So they're both correct. So it's just that the first value becomes x here, and here the first value becomes y. So just be careful while specifying that. If you're using comma, x, specify in the format of x, and then y, and vice versa when you're using tilde. Okay, but anyway, mostly the one with comma is preferred. So don't get confused, but it's just for your information. Now, the other arguments that you can specify to improve the plot. So by default, the x-axis label and the y-axis labels, these are the names of the columns or the name of the vector that you are using. But if you want to specify a better name, so you can say x lab is equal to, and then in double quotes, you can specify whatever the value is. Likewise for the y label. And again, if you want to give a title to your entire plot here, then you can just specify using the main argument. So this is what it's going to look like. There's also a font argument, and that's mainly whatever the fonts are, they're going to become bold here, or they can become a different font. So there are also these values, like what value indicates what font. Like the best source would be to Google it. But there's one more thing here. Yeah, so this one. So currently you can see here that each of the plots, each of the points is a circle, which is not filled. It's a non-filled circle. So by default, it's 1. The point shape, that's 1. But there are a lot of point shapes available. You can specify that using the PCH argument. So again, let's take the simple one here. So you can specify PCH, let's say 4, and you can see here these becomes crosses now. So you can specify all sorts of things. The best way to try what each of the arguments are and how you can change them is go to the help menu for this function. You can just say ?plot and then the generic xy plotting. So you can see here main, sub, x label. There are a lot of things available. And so sub, of course, it's a subtitle. Type here is what kind of plot. So by default, it's only going to plot points, which is this type P. But you can also make it as a line plot, or you can make a plot where you have both points and lines, or it can be a step sort of an arrangement, or it can be a histogram. So we'll see what each of them looks like. So this is what that is. So this, on the first one that you've seen, is the basic plot. The second one is where you're just connecting each of the points from left to right with a line. You're not making those, you're not plotting the points themselves, but you're connecting them by lines. And this one, which is B or both, you're making both points and lines. The one with S means you're making steps. So again, you are making a line, but these are horizontal, vertical lines only. And then in case of a histogram, you're actually making like a projection on the x-axis for each of the points. So it's not exactly a histogram, but it's just projections of each of the points. All right. Now, there are also some more sort of scatter plots that you can make. So, yeah, I think it's, so this is, it's like if you want to plot all your three variables together. So in this case, the three columns of the trees data set, girth, height, and volume. So it's basically making, so this is variable 1, 2, 3. So this plot is between variable 1 and 2. This is between variable 1 and 3. This is between 2 and 3. And here as well, it's the same 3 plots. So you do have 6 plots here, but these are just 3 plots and repeated twice. And another way of making the same thing is through, so you're converting the trees data set, which is a data frame, into a matrix. So as dot matrix, and then using the pairs function to do the same task. It's just that in this case, it's taking these values directly. In the first one, it was calling it variable 1, 2, 3. But again, so this is just an extra way in which you can make all the plots and print them together, but the information still stays the same. These are still going to be 2 variable plots or bivariate plots. Another thing you can do for these plots is fit a straight line or fit a curved line. So there are two. Okay, so for a curved line, there's a direct function. So again, so you remember for the plot function. So what the plot function is doing, it's making a new plot and it's plotting those points on that plot. Okay, using the x comma y or the y tilde x arrangement. Now, instead of making the plot, you can directly say scatter dot smooth, and you can fill this using, again, the x comma y arrangement. So the scatter smooth function, what it does, this is making the plot and the line. It's doing both the tasks. Now, but when you want to make a straight line, it's a two-step process. First, you plot the usual way. So this is what you've plot. And then you're adding a line to it. Okay. Now, to make a straight line, that's linear regression, right? So there is a function called LM, which stands for linear model. And the linear model has to be fitted between, again, the same x and y variables, but the arrangement it takes is y tilde x. So the y, whatever the y variable was here, and then tilde the x variable, you do the LM function on it. So the LM function is going to give you the intercept and the slope, right? So, and then what you do, you plot this information using the abline function. Okay, so once I plot the abline, once I type in this, the abline function is just overlaying this line on an already existing plot. It will put this line on any existing plot. So again, remember, the plot function is making a new plot and plotting the points. So this is what we're doing here. The abline function is just making a line on an existing plot. The scatter smooth function is doing both the things together. It's making the plot as well as fitting that smooth line. So yeah, so that's this. This can be a little bit confusing, so definitely give this a try. Once you've typed in and worked around what's working and what's not working, it should become simpler. Okay. And then again, of course, there is a way to make a 3D plot with three like XYZ axis. So it's not available by default in base R. So you can install this packages scatterplot 3D. And then of course you have to call the library. So, okay. So I have already installed this package, so I'm not going to do that again. Um, I'll call that library. And then if you want to make that plot, since the data frame already has 3 columns, we don't need to do any modifications to it. So scatterplot 3D, that's the name of the command as well. And then within it, we give it the trees data set, and that's it. It's directly able to plot that. So this is your volume, this is the girth axis, and this one is for the height. Again, it's not very, very obvious what's happening here. So it should definitely always prefer a 2-dimensional plot, but at least this is possible. And you can turn around this cuboid by 45 degrees, 120 degrees, whatever number of degrees you want. So it can shift. So whichever one you want as the front facing 2-axis. Okay. Do we have any questions up till this point? Okay. So the last bit here, let me see if we have something else. All right. So the last bit for this course is sort of like a big summary of the entire thing. So what we're going to do is we'll make a function. We've seen functions in the past. So we'll make a function. It's going to be a little bit complicated maybe, but so it should involve a lot of things that we have done so far. But other things that you have to take into account whenever you're working in R. No, it's not compulsory to give a table as the input. So now if you remember this case, like when we are doing call sums, so the arrangement here, so you see, this is actually a named vector. Okay, let me give you an example. So this is, let's say it's a vector, just a simple vector that we define. Okay, 1, 2, 3, 4. And then we can give names to the vector. So again, let's say I'm calling them element 1, element 2, element 3, and element 4. So now you see my vector A becomes a named vector. Now I can fit in bar plot A, and that's it. So you see, you've got those 4 categories, whatever the 4 names you said, and then the value associated with each of the names became the frequency value or whatever value for the y-axis. So giving a table is not important. Generally, it's a table because it's indicating frequencies. But if your frequency information is available as a named vector, then that's enough also. So let me just put this here as well. Yep. It's fine. So in general, the things that you have to consider and remember when you're working on R is these comments, which are given by after the hash symbol. These are important because they sort of tell you what you've done at that moment, because you might want to look at your commands after some time, and then these comments would help you remember what exactly each line or each chunk of lines was doing. And it's definitely advisable to not reuse a variable. So for example, in this whole thing, so if we have already defined, let's say, cat 55, 50 to 55, or if we already call something as a, we should not use a again. You can, it's just going to overwrite, but sometimes you may refer to it later and then it can get a little bit messy. Yes, definitely increase the readability of the code when you have comments. That's the correct description. Good. And so don't reuse variables. And today we'll just see an example of a function within a function. And we've seen the RM function in the past, right? The remove function. And it does the same job as this broom symbol here to remove your variables. Of course, this is there to be used, but you have to be careful. And we've not explored that in a lot of detail, but very often there are multiple ways of doing the same task. It's just that one is going to take more computational power than the other. It is not very obvious when you're working with smaller data, right? So if you were just using a plus b versus if you're using some a comma b, both the commands would take less than a second when you're running them. But when you're working with maybe larger data, and if it's a more complicated command, then out of the two different options, maybe one of them is 2 times faster or something like that. So just keep that in mind. If it comes into use sometime, then yeah, it's just good to know that things like this exist. And also for the nested function, so anywhere that you see more than one bracket within a bracket, all of those are examples of nested functions, right? So this here is also a nested function. And we've seen more complicated nested functions earlier, right? But yeah. So anyway, so today we'll see an example of a nested function that you are defining. So the task that we have is you have to write functions to calculate the standard deviation of two given distributions, and then you compare which is bigger and which is more or which is less. Okay, so just as an example, you can specify your own distributions, but there are a few ways in which you can define these distributions from within R. So let's say one of the distributions is a normal distribution, and the other one is a uniform distribution. There are commands in R to define that. So I'm saying make a normal distribution with 100 values, where the mean is 25 and the standard deviation is 10. So if I just run this command, you will see that x1, that's a vector, it has 10 elements. And so these are these 10 values. Now, here we already know that the standard deviation is 10, but anyway, you can plot this and see what it looks like. Likewise, let's define the uniform function. So for uniform function, it's basically just a horizontal line with a minimum and a maximum value. So let's say again, I need 100 values with the minimum being 0 and the maximum being 50. So this is what that looks like. So again, all values between 0 and 50, they have roughly the same probability of occurring. So you can make histograms. So a normal distribution, which is also called like a bell curve. This is what it normally looks like, and it looks roughly like that. You can increase the number of breaks to get a better distribution. But nevertheless, this is what a normal distribution looks like here. And the uniform distribution, so roughly it has to be like a straight line. The frequency of each of your ranges should roughly be the same. It doesn't happen perfectly, but like it doesn't happen perfectly when you just have 100 values, but it's somewhat there. All right. Now, there is definitely a direct command to find the standard deviation in R, but let's say that's non-existent. Okay, so the the more complicated form, let's say you actually have to make this command using the complicated form. So the way to find out the standard deviation for any distribution is, so you have these values, right? X1, X2, X3, and so on. The first step is that you find the average, right? So that's X1 plus X2 plus X3 and so on, divided by how many values there are. So that's N. That's the first step. Then the second step is you want to find the difference of each of your values from the mean, right? So X1 minus mean, X2 minus mean, X3 minus mean. That's what you're going to find. The third step is that you want to find the square of these values. So you square these values up. The fourth step is you sum up these values. So xi, you take a sum of all of these. And then the fifth step is whatever this value came, you divide it by n. Now this is going to give you the variance. And finally, for the sixth step, you can take a square root of this thing. And that's your standard deviation. So now again, the question that you have to address here, again, this is just for practice. I know it's a little bit complicated, but it's just as a practice. So you have to make a function which does these 6 steps. Then what you can do is you can run this function twice for each of your 2 inputs. It's going to calculate the standard deviations for both of them, and then you can compare if one is bigger or 2 is bigger. Okay. So this is the function here. So it's getting one input. That one input is going to be a vector. So what you first do, the first step, you find the mean of that vector, and I'm saving it as the variable avg. Then I can find the difference of each of my values to that average, right? So you remember vector minus a scalar, it gives you another vector where everything is just subtracted, like just that scalar is subtracted to each of your elements. And then you've got this. Now what you can do is you can square each of them up, and then you can sum it up. And then you want to divide it by n, so that n is going to be length. And then you want to square root. So these are the 6 steps, right? And then what you want is you want to return this output. The standard deviation that you calculated, you want to return it. So now if I run this command, you see the function _sd, it runs there. Now, as an example, let's say I say func sd and x1. So it gives the value 10.379. And you see, we asked it to give us a standard deviation of 10. So it's done a pretty good job that the standard deviation is actually 10. Again, instead of x1, I do x2. So now the standard deviation here is 14.5. So you can already see that if we wanted to compare the two standard deviations, we can say that the second one is bigger. But here we had to compare it manually. So we can define another function. So I'm calling it func2, and it's accepting 2 inputs. So the first input is going to be a vector, again, the first distribution. The second input is going to be the second distribution. Within it, you call the first function here. So within the second function, you're calling and finding out the standard deviation of each of your vectors, each of your distributions. And then using an if-else statement, you can say that if standard deviation of x that you just calculated, if that's bigger than that of y, then you print the distribution 1 has a larger standard deviation. Else, you say distribution 2 has a larger standard deviation. So if I execute, like, run this command, then you just need to run the second command. The first one is inherently going to be, like, it's internally going to be executed. Did I confuse you, or does it make sense? So if oh, it's good. All right, great. So I'm just running the second command here. I'll just call it func2 x1 x2, and see the final what it gave is that distribution 2 has a larger standard deviation. So that's it, right? So sort of this one kind of took into account a lot of things that we've seen throughout this course. Again, you can make it more complicated. The question can be that you calculate the standard deviation of the two distributions, you compare them, and then you plot the histogram of whichever is the one with the higher standard deviation, right? So instead of saying print, um, you can actually print the histogram of whichever two it is. So just the important difference between these two functions is the function underscore SD is returning a value, right? It's like the functions you're using so far. Like when you're saying sum A, B, C, D, it's giving you an output. So which is why there is a return function, return line here. So whatever that return is, so when you're running the command, you can save the output here. Again, you can use the assign function also, right? For each of them, you can use the assign function. So since you're assigning the output, it means there is an output, and that output comes up from the return line. And for func2, there is no output as such. You're not saving it. It's just plotting something here. So there's no return command here. Okay, so that was it. I think I have just just a couple of questions for you. So if you want to make this bar plot, and this is like it's a half code that's given in this question. Are you talking about question 1 or the question that we saw in the R studio? Um, okay. For this, like, ideally, there should just be one answer correct. In case you feel that there is more than one answer correct, then you fill in the one which you are 100% sure is definitely going to be correct. Like, for example, the one we saw, table, matrix, array, we saw vector and all that. So there's one which is definitely going to work every time, right? So fill in that one, because like, you can only choose one option in this question. So choose whichever one you think is 100% correct. Once the solutions are out, if you feel that the answer is incorrect, you can always put that up in the discussion forum, and it can be taken up in case there is something wrong. But for now, all I can say is think whichever one you think is fill in whichever one you think is definitely going to be correct. Okay, so this question is very similar to the one that you just pointed out. So if you want to make this bar plot, what's going to be the commands? What's going to be the blanks here? So X, Y, Z, and W. So do you want to give this a try? Hmm. Yeah. So So what do you think X here is going to be? Okay. So the data that you see here, so the data basically is 1, then, so it's sequence, right? So it goes from 1 to 48 and then in intervals of 2. So the data is like this, right? Up until it's going to go up till 47. Now so that is your data. And you see here, this is that bracket. So data, n row, n col, right? Now you can, do you remember where all do you have these arguments? Data, n row, n col, by row. What command has that? Matrix, yes. Right? So this has to be a matrix. So again, the question that you pointed out there. So we've seen that you can make a bar plot using table, using matrix, using a named vector. So all of them are correct answers, but depending on the question itself, you might be able to figure out what, in that example, what would the correct answer be. All right. So fine. So we have defined that, okay, this is going to be a matrix and we are going to fill it by row. So if you remember from the example we saw, this bar plot is actually a sort of a pictorial form of the matrix itself. So when you want to identify how many rows and how many columns were there, you can directly see. So how many columns or how many categories are there here? So you see that there are 6 categories. So this is same as, yeah. So 6 columns. And the colors here, so you have 4 colors. So that's equal to 4 rows. So this is 4, this is 6. And this col here, don't get confused, it's not column. This is colors. So what are the colors here? Do we go from top to bottom or bottom to top? What's the order in which we do that? And
Bottom.
Sorry, say that again.
Bottom
To top. And do we specify, like we say col is equal to, just put the name of the color, put it as a vector, put it in double quotes, what do we do?
Like into the round brackets.
But before that it has to be a vector. So
Yes.
C, right? And then we write blue, comma, then green, then the next one is red, and the next one is going to be yellow, and that's it, right? So yeah, so that's that. Good, that's nice. And this is it's just to see, so when you go from plot 1 to 2 to 3 to 4, what have been done here? How did you make this plot? So what sort of a plot is it? Just that. Out of the 4 types of plots we saw today, what plot is this? It's a histogram, right? So you use the hist function and sort of you can see here that it's a little bit complicated, but you can see here that this is the column that was taken. This is the set of values that was taken. So hist and this thing, sorry, yeah, hist of this whole thing, that's your column, or that's hist this thing. Fine. When you go from 1 to 2, what changes do you see in the figure?
X label has been added.
X label has been added, correct? Y label has also been added. and
Yeah.
a main has also been added. So title. So xlab, ylab, main. 3 things. Okay. Then when you go from plot 2 to plot 3, what do you think has changed?
Range of y.
So range is still the same. You see it's from 0 to 50,000. This is also 0 to 50,000. So range is the same. What
For
difference do you
y,
see?
y-axis.
Uh, yes, y-axis has been changed. But you see, the reason the y-axis has been changed is because you've made these breaks have changed. So what the y-axis is telling you is how many values are there in each of your ranges. So let's say this first range is from 0 to 5,000. So between them, there were, let's say, 4,600 observations. Now you reduced the range. So instead of taking from 0 to 5,000, you're taking from, let's say, 0 to 1,000 only. So within that 1,000, you just had, let's say, 800 observations. So the y-axis range changed because the number of breaks were changed. But good observation that the y-axis was changed. But that's a result of changing the number of breaks. Okay. Now, from plot 3 to 4, what has changed? No idea. Okay. So now you see here, the range has actually changed. The x-axis limits. So you remember we saw this xlim is equal to c and you give one value and then you give another value. So here the value was, like by default, all the values were between 0 to 50,000. And now you've specified 0 to 30,000. So it's still this plotting, it's just plotting this bit now. Okay. So, yeah. So that's it. So that brings us to an end for the last class for this course. As always, there's going to be one assignment due coming Wednesday. And we'll have a revision session on the 21st of October, Monday. The Zoom link will stay the same and you'll get an email for that. I think the exam is scheduled for 3rd of November. So for if you or anybody else is appearing for that, any questions you have regarding the exam would be better directed to the NPTEL team directly. But let me know if you have any other questions.
Okay.
Yep. All right.
Yes.
Okay. Thank you so much for joining. I'll stop sharing the screen. So all the best. And I hope this course was useful. And I hope these live problem solving sessions were also useful. So thanks for joining. Good night. Bye-bye.
Bye. Thank you.
Thanks.